Hello students, welcome back. So in the last session we have discussed about the inkjet 3D printing technology. So we have discussed what is inkjet 3D printing technology, what is the characteristic of that technology, what are the different types of inkjet 3D printing technologies uh, and other things. So in this lecture we'll be discussing what are the different types of biomaterials used for this inkjet bioprinting technology, or what are the characteristics that certain biomaterials should have to be applied them for this bioprinting technology. So as you have must have been seen, the inkjet printing technology is on nothing but the generation of droplets and then delivering them to the substrate or printing stage. So here, for generating droplets, the biomaterials should have a certain level of viscosity. So typically the viscosity of the biomaterial solution or the formulation have like water like viscosity, or have very low viscous materials can be used. So the viscosity, as it is mentioned here, viscosity of in the range of 3 to 30 millipascal second, that range of viscosity is very suitable for inkjet 3D printing technology. So the biomaterials of this range mostly used for this technology. Similarly, surface tension is also a very important process parameter for this inkjet bioprinting technology, and the surface tension typically for this biomaterial formulation should be in between 20 to 70 millijoule per meter square. Okay. And the density of the material should be around 1000 kg per meter square. So these are the recommended values for a biomaterial formulation or pharmaceutical formulation to be used for inkjet 3D printing technology. But this inkjet printing is a quite versatile technology. Both Newtonian and non-Newtonian fluids, with of course with suitable fluid properties, are mostly used and can be used. And we can actually basically we can use different types of solutions, different types of formulations we can use with inkjet 3D printing technology. Either we can use aqueous solutions, like either the materials is material dissolved in an aqueous medium, similar like some hydrogel or any aqueous solutions. Similar organic solutions, where suppose the material, biomaterial or the pharmaceutical material that is dissolved in some organic solvents. So that is also possible. Those are also possible. And similarly, not only solutions, the suspensions can also be used can be used as a material for inkjet 3D printing. Suspensions like that are containing metals, ceramic or polymer microparticles. So when these microparticles are suspended in a particular medium, then that can also be used as a material or biomaterial for inkjet 3D printing. Similarly, certain cases, few researchers, they have also used composite microcapsules like gel matrix and dispersed solids with a relatively high solid content. So a few researchers have also shown the capability of using this kind of material for 3D inkjet 3D printing, right? But when we talk about inkjet 3D printing, then what happens? Because the nature of the process is such, during printing or during the when they are inside the nozzle, that time they should be in the solution state or liquid state, right? But as soon as they come out of the nozzle, and when we place them or we deliver them to the printing stage or substrate maybe, then they should have been, means like that time they should be the transform into a solid, or from the liquid phase they should be converted transformed into a gel state or liquid solid state. So uh, that capability should be there when a biomaterial formation should be used for inkjet bioprinting. So biomaterials should offer at least any ways. One such ways are for solidification, so that after printing the structure that is stable, the structural fidelity, that means the way the structure is built, that should be maintained. And actually various physical or chemical approaches have been used for to achieve the solidification process, so that the structure gets stabilized. Something like absorption. So suppose after printing or after the generation of droplet and placing them on the stage or the substrate, they should get absorbed very fast. So by this way the solidification can achieved. Diffusion. So suppose there can be a diffusion of the molecules or diffusion of ions. By this the maybe the gelation or the solidification can achieve. Again, the solidification can be achieved by various other means. There can be, suppose there can be electrostatic interaction. Because of this the formulation that gets solidified. There can be hydrophobic interaction, there can be covalent bonding, suppose, and also there can be hydrogen bonding. So all these different types of approaches can be used for transformation of the liquid drop to solid, so that we can actually basically we can go for use this inkjet 3D printing for printing 3D structures, right? So these are the different different properties of the biomaterials that should be there for to be used for inkjet 3D print. Now specifically we'll see what are the different types of biomaterials those have been used for inkjet 3D bioprinting. The very first example is the hydrogel. So hydrogel is a material, is a aqueous based material. When suppose the material is there inside the aqueous system, and then that absorb water without getting actually dissolved into the system. So right, so different types of hydrogels are being used, and mostly these materials are used for different other applications, and then those are being tried for inkjet 3D printing. Like alginate is one such material. It's a hydrogel. So it is also very well, it is used, and it's a widely used biomaterial or hydrogel for different applications. So that different, and along the same line, this has also been used for inkjet 3D printing. Similarly, polyethylene glycol, this is also a synthetic polymer that is used for things. Similarly, hyaluronic acid, chitosan, silk, collagen. You can actually, the list is very long. So you can different types of hydrogel materials are used for inkjet bioprinting. But we need to consider the viscosity of these materials, because the viscosity should not be very high. A low viscous this kind of materials can be very well used for making either making 2D patterns or making 3D structures, or patterning of these biomaterials, making different types of 2D patterning. Those things are very much done. Right? The next class of materials are the binders and powders. What happens, this inkjet printing technology can also be very well used for, suppose, for making structures with powder bed. Suppose we make a powder bed first, and then with the inkjet printing head we sprayed the binders. So what will happen, the binders, when they come out of the nozzles as a droplet, those droplets will go and attach, or the droplets will go and stick to the powder bed, and there we control their positioning. Suppose we control the positioning of these droplets, we put them at certain locations of this powder bed, then what will happen, these binders will go and bind the material or the powder material at those specified or pre-designed location or coordinates. In this way also we can prepare 3D structures, right? So that's why different types of binder materials are used, and this can be also done by two ways. Either the solid or the dried binders and powders are mixed together, and then those are placed on the stage. Then the aqueous droplets are big. Suppose aqueous or bind droplets are either it can be aqueous or organic. Then those droplets are being produced, and then those are basically sprayed on the this thing. Now what will happen as soon as this aqueous or the solid liquid medium, aqueous or organic liquid medium, that touches that powder bed where the binders are already pre-mixed, then they will dissolve the binder, and then the binder will bind the powders. Or the other way is we can spray the directly, we can generate the binder droplets of the binder solution, and then that can be used for making 3D structures. So there are different types of binders, and this technology is very well used or widely used for pharmaceutical doses preparation or development of different pharmaceutical doses like this. The mostly used or widely used binders are like acrylic ink, sodium carbonate sulfate, phosphoric acid, polyvinyl alcohol. These are the widely used binders, but there are many other examples available in the literature. Similarly, few of the powders, widely used powders are like tricalcium phosphate, tetracalcium phosphate, dextran, polyethylene calcium silicate. These are the most commonly used powder materials. So here the concept is using a powder bed, we put the binders from the using this inkjet principle where the droplets are generated from the view of these binders, and then those are getting spreaded or delivered on the powder bed, and then powder bed those binders are mostly mass binders bind the powders at certain locations, and then what happen, then we generally solidify the whole thing, solidify after that we solidify them or stabilize them by heating. Upon heating, what will happen, these powders will get fused with each other, and the unbound powder, after this inkjet printing, unbound powder we can easily remove them because those are loosely attached, so we can easily remove them. And the bound structure, what are the structures that is built by these binders, that structure is can be heated up, and then we can get the final product. Similarly, in inkjet printing, various polymers are also used. This is just, I have written here only 4 examples like PCl, polycaprolactam, polyurethanes, polylactic acid, polylactic or glycolic acid. Similarly, there are various types of polymers. Either it can be aqueous solvent or it can be organic solvent. Where all these different types of polymers are mostly used. But the most important thing is these polymers are made solubilized first at certain and some solvents, like either it can be, if it is aqueous polymer like PLGA and others, so those can be made soluble into aqueous solution, or other PCl or others organic, suppose they can be made into soluble into organic solvents, like something like they can be made into chloroform or other solvent, and then polymer solution can be used as a material for inkjet 3D printing. Then the same phenomenon where these polymer solutions can be loaded into the cartridge. Through that, from the cartridge, it will reach to the nozzles, and from the nozzles, based upon either it can be a thermal or it can be a piezo, the droplets will be generated, and then these droplets are basically then plotted. Now, when we use polymer solutions, if it is organic solution and if it is a volatile solvent, then the solidification process would be much easier, because after the printing the solvent can be easily evaporated, and then we can get the solid either solid particles or solid structure. But when we use aqueous solvent, then we need to take care how these polymers can get again solidified, and then we can make the structure. So to improve the stability of the structures, we need to use either one or other solidification strategies that we have discussed in the earlier slide. Similarly, various small molecules can be used, like various biomolecules like other growth factors, peptides, uh, DNA, different proteins. So these are various types of, even the different pharmaceutical materials, like suppose different pharmaceutical drugs, the combination with excipients or other stabilizing agents, And similarly amphifiles. So all these different types of small molecules are also can be used as a biomaterial for inkjet 3D printing. What happens here, because this inkjet printing technology, it has the capability of patterning into a 2D structure. So that's why this kind of molecules can be very well used for, suppose, for 2D patterning, even for 3D patterning, even making different types of, suppose there's a gradient, making a gradient structure with different materials. So that can be that kind of things also can be very well used. So these are the different types of biomaterials. Those are most commonly used for inkjet 3D printing, and there are various other there are many other biomaterials. Those are also being used, but these are the major class of biomaterials. Those are used. Now this is a diagram of a 3D inkjet 3D bioprinter. If you see closely, this looks very similar to your office printer, right? So in our office printer also looks like very similar to this. That, of course, the office printer can be either based on the principle, can be based on inkjet, or it can be laser, but inkjet office printer will be similar to all this thing. But here there are a few differences. First we will see what are the different components of this inkjet 3D bioprinter. If you see here, then we have this printed, right? This printed is the here where the nozzle modules or the different nozzles are lined up within the printed, right? And this printed is attached to the 3-axis motion control stage. So that is the printing stage, right? Where it can move in all x, y, and z direction, right? So it can move in either x, y. So it can go to any coordinates in x, y, and it can basically print the droplets. Or also it can also, suppose if you are making a 3D structure, say suppose then at the beginning this printed will be somewhere at this level, and then when the first layer is done, it will go up one layer, and then again the next layer will be printed. So this can also go in XY, all XYZ movement can be possible of this printed. Similarly, now there are two changes here. In our this printer, we have used some cartridges where some inks are there for printing suppose for printing few text or maybe printing images, right? But here that ink that has been replaced with a bio ink, because the bio ink, it may contain cells, it may contain biomolecules, it may also contain biomaterials, whatever we have discussed in the last slide. So those things are basically can be put inside this, and then from here it reaches to the print head where the nozzles are there. So it reaches to the nozzle, and then they fill the capillaries there, right? And then based upon any mechanism, either it can be DOD or it can be thermal, the droplets will be generated. Again, another change is the paper tray has been replaced with a plate or printing stage, where we can actually basically we can keep either our printing substrate. So on that, so that we can print directly on the substrate. Also, we can print directly on the printing plate or anything, right? So this is a typical diagram of a inkjet 3D bioprinter. This looks very similar to our office printer. Let us see what is the use. The one important thing to remember for of using any 3D printer or any 3D bioprinter is that they work on certain process parameters. So there are certain process parameters that we can control while using this kind of printers for certain applications. Like these are the process parameters for inkjet 3D printing, like viscosity of the material. As we have already discussed, in case of inkjet 3D printing, the viscosity of the material cannot be very high. So we use some low viscous material, and in this particular range, like 3 to 30 millipascal second. So in that range of viscous material, we can definitely use for, as I said, viscosity of the material should be in that range. Again, surface tension. Now surface tension is important because when the nozzles are filled with the material, though in the nozzle the printing nozzles are open, the material generally doesn't come out of the nozzle from that liquid column, because the surface tension of the material prevents leaking of the material from the printing chamber, right? So whenever there is a pressure pulse, only that time only the material or the droplets come out. Before the droplets generally don't come out. So surface tension play a big role here, and there is always the and the surface tension should be in that range between 20 to 70 millijoule per meter square. So in this range of surface tension material of surface tension we can definitely use. Again, density of the materials is very important. Suppose the material what density because in inkjet 3D printing generally we generally don't prefer to print a highly dense structure, highly dense material. So the density is somewhere like 1000 kilogram per meters cube is can be very well used, right? Then the next thing is the nozzle diameter, and we have already discussed this in the earlier section that in case of thermal inkjet, the nozzle diameter is around 50 micron, and in case of piezo, it can go a little lower than that. So the nozzle diameter is an important process parameter, and depending on the nozzle diameter, the generated droplet size is uh, related to the nozzle diameter. But we need to remember another thing. We need to remember that if the nozzle diameter is decreased, we can produce very fine droplets, but there will be high chance of nozzle clogging, right? So that's why to prevent the nozzle clogging, the nozzle diameter is generally kept around 50 micron. It is not kept below that. So but nozzle diameter is important process parameter, and but we can control the we can change the nozzle diameter, and we can produce different size droplet. Another nozzle type is also very important factor. What type of nozzles are basically you are using, depending upon the droplets, generated droplets will be of different properties. Then print speed, at what speed you are basically printing or the printed is moving, that is the print speed. So that should be depending upon your firing speed. That means at what speed or what rate the droplets are coming out, right? So you always, there should be a relation between the droplet ejection rate and your print speed. These two parameters should be always matched. Otherwise what will happen, you are moving your, suppose you are, if your ejection rate is very high but your print speed is low, what will happen, the drop more or a huge number of droplets will be delivered to a certain location. Then they can again they will fuse with each other, so you will not get a good distribution, right? But if your print speed is matching with that, then you will get a very good distribution or very good pattern of these droplets if you can do this. The other case, suppose if your print speed is very high, your ejection rate is slow, then what will happen, your printer will moving is very fast, but the droplets are not coming at that speed. So what will happen, you the droplets will be sparsely arranged, sparsely patterned, or just sparsely arranged on the printing stage. So in both cases, you will not get the ideal or the design structure that you have suppose you want to make. So these two, injection rate and print speed, both these things should be very well matched for to get a proper structure or proper pattern or proper geometry. The other thing is for thermal injet the heater temperature. All this the signal that is giving to the heater. So that is very important. So heater temperature, what temperature you will be use, because we cannot use very high temperature. Then it will be detrimental for the. Suppose we are using some biomolecules, some bioactive factors or cells, then it can be detrimental for those. But if your heater temperature is also low, then it will be not that much effective. So you have to have a balance between this thing. So heater temperature can be controlled, it can be kept at a certain temperature at a certain level, so that you can get that what the it is not detrimental for the encapsulated or suspended particles, suspended cells or biomolecules or just this thing, but it should be enough for efficient droplet production. Similarly, for piezo inkjet bioprint 3D printing, they are the signal for this for generating this thing. Like the voltage, current, frequency of the electric signal. That is very important. So that in other way, the vibrational frequency of the piece of material, that is very important, because it has been seen, or it has been observed, that if suppose the piece vibration frequency is very high, like in the range of, so suppose 15 to 25 kilopascal, then it is detrimental for cells, right? Below that it is fine. So that's what we have to control. We have to control the frequency of this vibration. So those things. So these are the process parameters. There are a few more process parameters, but these are the most important process parameters then you need to take care of before actually going for printing with the inkjet printing. And for different biomaterial, actually you need to optimize this process parameter. And this comes with trial error method. You start with setting up some process parameters, see how the outcome is, and then you can change one at a time, and then you can actually control, or you can optimize all the process parameters to get a desired inkjet printing process. Let's come to the applications of this technology. Actually, there are various applications of this technology, and nowadays the inkjet printing actually widely used for all these applications, like either for polymer molding. So where suppose polymer molding, where we use polymer for either for molding application, or making 3D structures, or making 2D patterning. All these different applications can be there. For preparing nano composites, also nowadays the inkjet bioprinting, inkjet 3D printing is used, where suppose you want to make nano composites, because the nature of this printing technology is it can create droplets, very fine droplets. So differently, by creating that fine droplets, we can create very fine structures, or very fine particles, right? Now when we do this, like suppose you want to mix two three materials together, that then we can mix them together, and then we can generate these droplets, and then generate the particles. So where we can get the suppose the composites can be of nano dimensions, composites can be very well prepared. Similarly, for drug delivery applications, either it can be for drug screening, it can be for drug delivery. So these for various applications also, this inkjet 3D printing is used. Similarly, for tissue engineering, where suppose our interest is to make cell patterning, our interest is to print biomaterial pattern, or it can be 2D pattern, it can be 3D pattern. For all these things, for different tissue engineering applications, this inkjet printing can be used. Similarly, for cancer modeling or disease modeling, also 3D inkjet 3D printing is can be used. And then is an recently developed, it's an upcoming area where there are various research groups working on this cancer modeling thing. Now let us discuss specific applications of this technology. Like suppose for pharmaceutical development, as 3D printing, inkjet 3D printing is capable of producing droplets of controlled size with in a high throughput manner. So this technology can be very well used for generating droplets, or creating patterns of droplets. So that then later on what will happen, these droplets can be very well used for generating, suppose generating particles, or generating particles, or generating spots with drugs, right? So these spots can be created at a very high throughput manner, in a controlled manner. We can have array of these things. Then now these spots, or these arrays, can be used suppose for screening of molecules, right? So that's for drug screening. This technology has got huge applications, and this is very well used. And nowadays various pharmaceutical industry, they are interested with this high throughput drug screening, and this technology is widely used for that application. Similarly, for drug formulation, so suppose our interest is to make certain drug formulation, what we can do, suppose the drug active pharmaceutical ingredient that has some pharmacological effect, that can be very well mixed with certain APIs. That means active pharmaceutical ingredient that can be mixed with certain excipients or some adjuvants, and then that mixture, suppose that mixture can be used in inkjet 3D printing, where the droplets are created with this technology, and those droplets will be dried up, and then again we can get this formulation or the drug plus active formulation, that mixture thing. So this kind of formulation, drug formulation, either it can be nano capsules, it can be nano tablets, it can be different types of formulations can be very well developed. So in pharmacy, this drug formulation also nowadays inkjet 3D printing is widely used. Similarly, other thing is drug coating. Suppose the certain drugs, they are very much reactive to the certain environment, certain conditions. So the coating is an important phenomena there, where the drug can be, or the drug can be preserved, or the drug can be controlled, or it can be preserved. The other thing also, it can be suppose our interest is to coat the drug, coat certain drugs with some material, so that the drug can be, or the drug is dissolution can be prevented at certain areas. Like, so for this kind of application, drug coating can be used. And at this stage, it is like the drug can be coated at a very relatively lower scale, so that the kind of nano coating can be done, right? Similarly, for drug delivery system development also, this inkjet 3D printing is very well used. The other application is biomaterial patterning, that we have already discussed in the earlier sections. Like, when we use different types of biomaterials, it can be either, it can be, as I said, it can be aqueous soluble, organic soluble, or it can be a suspension, it can be a mixture, all these things, different things. Now when they are used, they can be patterned, or suppose they can be patterned on 2D surface, where the biomaterials can be different surface patterning can be possible. Either it can be 2D pattern or 3D pattern, that those are possible with biomaterials. And they have got huge applications for different things. Either it can be used for tissue engineering, it can be also used for drug screening, it can be also used for different other applications. For preparation of scaffold without cells, in the same way, like, either we can use different biomaterials for preparing 3D scaffolds with this technology. Basically, when we create a digital file, from there the digital file can be converted, that can be loaded to the printer, and then the printer will take up the design, and then it can create that scaffold by generating droplets. But these droplets will get connected to each other, and then the layer by layer manner, as in the earlier section I have discussed. First we can create one layer, then the next layer by layer fashion we can prepare the cell-free scaffold. So in this case, suppose the cells are not used, only the scaffolding materials like biomaterials are mostly used. Similarly, for biomolecule inkjet bioprinting, like, we can create a 2D biomolecular patterns or 3D biomolecular patterns, where suppose our interest is to, suppose the proteins, we use proteins or any other biomolecule, and then we create a 2D either 2D patterns and 3D patterns. Then we can understand, we can do various studies. We can do some fundamental studies, suppose how the cells responds to us this biomolecular patterns, or any other type of studies can be easily done. Similarly, DNA inkjet bioprinting is another pattern where 2D inkjet patterning, either like DNA microarray you can create, or DNA droplets also we can create. So this DNA inkjet bioprinting also very popular, and this also an area where there has been huge amount of research done or going on. And then of course, for cell inkjet bioprinting, because the inkjet bioprinting is very popular for cell printing, because this technology is a one first thing is this non-contact method. It's a drop-on-demand technology. The next, so there really less chance of contamination, and different cells can be patterned in different way. The other thing is this, because we can also create droplets where single cell is there. Also create droplets where multiple cells are there, and then later on that can be also used for creating for other kind of like maybe a spheroids or other type of things can be also be possible. So either we can create a 2D cell patterns where the cells can be patterned in 2D, and then we can understand various some fundamental studies can be done. Also, some applied things can also be done on that. Similarly, 3D cell models can also be possible. Like suppose by printing one layer at a time, we can create a 3D structures for with the cells. So those kind of things can already well use. Similarly, for transfection, so for either for transfection of cells or with small molecules, this inkjet printing very well used. So inkjet printing technology for transfection, also inkjet printing technology very well used. There are some challenges with this 3D printing technology, with this inkjet 3D printing technology. The very first challenge is the nozzle clogging. That's a problem, and it happens because the nozzles are of very small sizes, like around 50 micron or less. So that's why nozzle clogging is a frequent phenomena. But it happens mostly when if you have suspended some materials within the solid within the medium, then what will happen, that the suspended particle can settle down and that can clog the nozzle. Of course, in certain cases, suppose the particle size of the suspended thing is close to the nozzle size, then also that can cause a problem. So nozzle clogging is a problem, and it has been tackled by various ways. Either suppose we can the if the suppose if the mixture is under agitation within the nozzle within the syringe, that can be one thing, and so various other things are there. Other thing is the not every biomaterials can be used for with inkjet bioprinting. Suppose we cannot use high viscous material here, so that can be a challenge. But of course we can also use a array of or wide range of biomaterials are possible. Other thing is printing 3D structure beyond certain height is a challenge with this technology, because this is here the droplets. With droplets we can make a 3D structures. So that's why we need some supporting material, like as I have mentioned already, some biopaper are mostly used. Even with them also, printing a 3D structure is always a challenge with this technology. For 2D patterning, for up to certain height, this technology is very good. So in this lecture, we have learned what are the different biomaterials we have can be used for inkjet 3D printing. What are the property? What kind of properties they should have to be applied for this technology. Also, we have discussed what are the different applications of this technology and along with these challenges. Thank you very much.